Go into chapter 3. You are going to like this. There's a lot of algebra in 3.1, of course, the part that I really like. And I'll try not to go too quickly. I'll try to keep it clean and neat. Be certain that if I'm going too quickly, that you say something, or if it's not as clean as it should be certain you say something, and I will definitely slow down and correct that situation. Let me turn this at an angle a little bit. So we're looking at section 3.1, which is called Tangents and Derivatives at a Point. Okay, tangents and derivatives at a point. And it's going to feel kind of like the same stuff we've been doing all along, but it is actually an advancement, but it's not going to really feel like it's something terribly new. Now, a little bit of what we have done and kind of what we're about to do, I guess we can call this something of a review, is if we refer way back to section 2.1, we talked about the slope of secant lines, which would kind of take us to try to get close to the slope at a point on the line. And when we did this, we were given this quotient to work with, and we did this on the test. So this is very recent in your mind. And this is what we did. And so we would go through and we algebraically determine all this. This was a question on the test. We went through and we algebraically worked all this, and we would come up with something like this. Okay, something that had h in it. And then we literally just kind of waved the magic wand and said, let h be 0, or let the distance between the 2 points that are creating our secant line, let's make that distance so small that we're going to claim it 0, and just kind of literally wave the magic wand and let h be 0. And then when we did that, we had 2 times 0 plus 3, and so we claimed the slope of the tangent line at the point equal 3. And again, we were doing a lot of just kind of making some very big assumptions. Now, what we're going to do in this section is we're not going to make such a big assumption, because now that we know how to take a limit, we're going to pretty much do the same thing, but now we're going to say that the slope of not the secant line, but the slope of the tangent line is not just say h is 0, but look at this as a version of a limit as h is approaching a value of 0 of what they refer to now as the difference quotient. So it's almost identical to what we were doing above, what we did like in section 2.1. But now we're going to find the slope of the tangent line at the point by calling it or by working with it as a limit as h is approaching 0 rather than kind of waving the magical wand. This is going to feel like it's the same thing you've been doing in the past, and that's why it's going to seem easy today, because it doesn't feel like it's so much of anything new. But the new part is the fact that now we're working with this as a limit rather than just making the assumption that we can just let h equal 0. So again, what we're talking about, this is the slope of the tangent line. This notation is finding the true slope of the tangent line to the curve, the original function, the curve, the original graph of some function at a particular point. Okay, so finding the exactness of the slope of a curve at a particular point on the curve. Now the curve, of course, changes at every point, so the slope of the tangent line varies at every point along the curve. And we'll talk about that in a little greater depth as we kind of move through some examples. But the big change is now that we know how to calculate a limit, we're now going to find that slope of the tangent line using our ability to evaluate a limit. Okay, so part B. Here we go into some examples. And I'm going to need quite a bit of room to do this first example. Okay, quite a bit of room here. So I'm going to have to turn the page. So give yourself a little space on this lovely question we're running into. And I will try extra hard to not make a mistake while I'm writing in pen, which I'm not very good at. Okay, so here is the question. Find the slope of the tangent line to the curve meaning the graph, the function, the graph of the function, and the curve is y equaling 1 over x at any point x. Okay, so what's going to happen is we have this curve y equal 1 over x, and we're going to evaluate the limit of what they claim now to be a difference quotient as h is approaching 0, and we're going to come up with an algebraic expression. And that algebraic expression is going to have a variable in it. And any number we put into that variable will give us the slope at any point along the line. So we're going to get an expression that's going to tell us the slope of the tangent line anywhere along the curve, so we can use it to put a number in to evaluate that true slope value at any point along the curve. Now, if we're going to find this, the new notation, and if you have ever seen any calculus, you'll recognize this. This is now referred to as the first derivative of the function, which is f prime of x. That's the new notation, f prime of x, which is the same thing as the slope of the tangent line to the curve, which is now going to be evaluated as the limit as x is approaching, as h is approaching 0, of what they now refer to as the difference quotient, x plus h minus f of x all over h. Okay, so we're going to substitute in all of this and find the limit as h is approaching 0, which h is like the difference, is the distance between 2 points of the secant line. We're going to shrink it down to no distance between them when evaluating the limit to get the exactness at a point. So we need f of x plus h as well as f of x. Well, with this function given to us, if I replace y with f of x, my f of x is 1 over x. To get the f of x plus h, to then substitute into this quotient function here, this is going to be 1 over x plus h. So those are the two values I'm putting over here in this difference, this quotient function. So now here we go. The slope of the tangent line at any point along this curve is the limit as h is approaching 0 of f of x plus h, which we just said is 1 over x plus h, minus f of x, which is 1 over x. There's my f of x plus h minus my f of x all over h. So now we have to algebraically calculate this limit. We know we cannot use direct substitution because it gives us a 0 in the denominator. So we just kind of go in here and manipulate this algebraically and see what we can make happen. Well, this numerator has two fractions in it whose denominator is not the same. So I'm going to get a common denominator and collect these two fractions into one. Well, the common denominator is going to have to be x times x plus h. So this is now going to be the limit as h is approaching 0. The new denominator in the top of this complex fraction is going to be x times x plus h. There's the denominator of the first fraction and the denominator of the second fraction. So now I have to figure out what those numerators are going to be. This first fraction in the numerator of this complex fraction, what does its new numerator have to be here? X. And the way that we determine that, and I know you know this, but I'm going to put it in here anyway, is if I multiply the top times x and the bottom times x, I get that new denominator. So x times 1 puts an x right here. The second fraction, in order for the denominator to become x times x plus h, I multiply this times x plus h over x plus h. So I'm multiplying by something equivalent to 1. So this numerator becomes x plus h. So I got a common denominator in the top of this complex fraction. So this becomes now the limit as h is approaching 0. And in the top of the complex fraction, you now have a denominator of x times x plus h and a numerator of x minus h. So you're going to distribute the subtraction. So this becomes x minus h. Kind of hard to see the steps, but there's the first one, there's the second one. So now this is the limit as h is approaching 0. X minus x is no x minus h. So I have a negative h over x times x plus h all over h. still a complex fraction. And remember, you want this h down here, you want it to go. You want to get rid of it because that's what's causing the issue with substituting 0 into this complex fraction, this difference quotient. So now what I'm going to do legally is multiply the top and the bottom times 1 over h, which makes this multiplication by 1. So when I do, I now have the limit as h is approaching 0, and up on the top I have a negative h over x times x plus h times h. That's all here. And in the bottom, that just turns out to be 1. All of that's really just over 1. And I guess I could put that in here. I do have the space. So finally, I get h's to reduce out. So now I have the limit as h is approaching 0 of really a negative 1 over x times x plus h. So I collected the two fractions in the numerator by getting a common denominator. Then I kind of cleaned up the complex fraction, which was able to get the reduction of the h. So at this point, I can use direct substitution. Now if I plug in h of 0 in, this is 1 over x times x plus 0, which is a negative 1 over x squared. So my conclusion is the slope of the tangent line to this curve, y equaling 1 over x, is the expression negative 1 over x squared. Now, you pick any x value, I plug it into this, and it will tell me the slope of the tangent line to that curve at that point. So this gives me the slope of the curve anywhere at any point along the curve. So now, that is the slope of the tangent line to the curve. So at this point, if they were to continue to ask me another question, they could say, so now that you have this expression, what is the slope of the tangent line at the point, say, 2, 1/2? Let me get a little higher, huh? What is the slope of the tangent line to the curve at the point 2, 1/2? So trying to get a vision of this, remember your original curve is y equaling 1 over x. Which looks something like this. Okay, this is your original curve. Your original function was f of x equaling 1 over x, and there it is. So now we're saying, what is the slope of the tangent line to the curve at the point 2, 1/2, which is this point right here? What is the slope of the curve at that point, or the slope of the tangent line to the curve at that point? So you're looking for the slope pretty much of this line. Okay, of that dashed line, to that point right there on the curve, 2, 1/2. And to find that very easily, we have the slope of the tangent line, and now what we're going to do is we're going to have this new notation, which is going to be the slope evaluated at the x value of 2. And this is kind of a new notation, which is really handy so you know what you're doing. The slope of the tangent line at the x value of 2. So we have negative 1 over x squared, replace the x with 2, and square it, and the slope of that tangent line is a negative 1/4. So this dashed line, which is the tangent line to this curve at that point, 2, 1/2, even just our sketch here shows that it's not very slanted and shows that it's a negative slope. So we should be on track. This should be a pretty darn good answer. Okay, we look good here. Now the other question they're probably going to ask, and let's see if I can fit it at the bottom of this page, is what is the equation of that tangent line? The equation of tangent line to the curve at 2, 1/2. Now when they say the curve, When they say the curve, that means the original graph given to you, which was the y equaling 1 over x. That is your curve. They often call it the curve, the original graph. So to do this, you now have the point 2, 1/2. You have the slope negative 1/4. So this becomes very easy. It's y minus y1, which is 1/2, equaling the slope, which is a negative 1/4, times x minus x1, which is x minus 2. And so as I am running out of room at the bottom of this piece of paper, it should be a negative 1/4 x plus 1/2 plus 1/2, so that makes it plus 1. Okay, so I'm like skipping a lot of steps in order to make it sit on the bottom of this page. Right? So that means that the equation of that dashed tangent line is a negative 1/4 x plus 1. That dashed line. And the original curve is this thing with a vertical asymptote at the y-axis and the horizontal one at the x-axis. You're going to do this repeatedly. They're going to really want you good at this. So you're going to see a lot of questions in the textbook and in homework that's going to emphasize these three things we just did at this question. So you're going to do this repeatedly until you get what we call darn good at it. Okay, very good at it. Now, this is going to seem very elementary to you, probably, but I do feel like I need to talk for just a minute to remind you, to refresh you a little bit about slope. You know, you go through your early algebraic classes and you just kind of do the steps your teacher tells you to do. But I do want you to have a true understanding, just a general understanding of what all this means. I know you understand what the slope of a line is, but you need to have a good perspective on it. When someone says the slope of a line has a slope of 1, what do I do with my straight edge? Little piece of plastic. I know not. Okay, it's this one. Something that has a slope of 1 is a graph that's going to go like this. Okay? If you have a slope of 1, you are a 45-degree angle to the x-axis. That line, yes, has a slope of 1.
Okay, so this doesn't really have anything to do with this. Before, remember how you said that it doesn't, h is not going to equal 0 now? Is that after this review? That h won't equal 0 for the...
Well, we did make h equal 0. Sort of. How far? We are... Back in section 2.1, we just waved the wand and said h is 0. Now we're saying look at it as a limit as h is getting extremely close to 0, which is much more technically correct, detailed correct. So we're still kind of doing, we did substitute a value of h in as 0.
But is it
That's how you wave the wand and use the limit.
Yes, it's it's pretty much the same thing because they didn't tell you anything about limits before we got to this section. So it's kind of weird the way this author approached it. You know, he did the little magical wand thing, and then he says, this is really what you're supposed to do. Yes.
When you multiply by 1 over h up there,
Yes.
on the next step after that, why is that a negative h on the bottom? How did you get a...
Right here? Right here? This one?
Oh. Okay, never mind.
Oh.
I thought that was a negative h.
It's a cursive H. Is that the answer to the question? Okay. Any other questions? There's a lot of information on this one piece of paper, right? A lot of room there for questions. Okay, so back to kind of the task at hand. When someone says a line has a slope of 1, you should be looking at that perfect 45-degree angle. It should cut quadrants 1 and 3 exactly in half. That should always be kind of your home base when you're thinking of something having a slope. If it gets less than that, and you'll know if you have less than a 45-degree angle, at this point, you really don't know what this slope of this line is, okay? You can just kind of guess it, but your guess should be it better be less than 1. That's your whole projection, is it's just less than 1. I don't know, maybe it's a half, maybe it's 2/3, but it's less than 1 to kind of keep you on track. When it gets to be more than this, then your slope should have a number bigger than 1. I don't know, maybe it's 3, maybe it's 10, maybe it's 3/2, but everything should be founded on knowing that the 45-degree angle is where you have a slope of 1. If you're less than 45 degrees, then your slope is a number less than 1. If it's more than 45 degrees, it's some number bigger than 1. So that you kind of know if you're in the ballpark when you're coming up with these values. So it's very simple. I know you know that, or you thought you knew that. Okay. Now you should know that, and you should know that very well. Be good at it. Because what's going to happen, and I will show you kind of what they do a little bit in the textbook, and like I said, you don't have a textbook, which is fine, but just let me show you very quickly some of the kinds of questions they start to throw at you when we get in this part of the book. And I'm pulling this up on page 105. They give you these graphs, and then they ask questions like, come on, focus, little camera. There you go, okay. Then they say, well, just go in there and make a rough estimate of the slope, okay? Make a rough estimate of the slope on the curve at the points. So they say, well, look there at point 2. What do you think the slope of the tangent line to the curve is at point 2? Wow! Okay, and it's a rough estimate, and the answer's not going to be in the back to check it because you all are going to come up with a different value. But if you were trying to guess the slope here, very obviously that is a lot more than a 45-degree angle to the horizontal. So you know that thing's got to be bigger than 1. And what you probably would do is go ahead and sketch a line like along my card, and then you would calculate the rise over the run, and still every one of you would come up with a different answer, but every one of you better have a value bigger than 1. It's just that basic. And then they want you to do it here too. So really what you would do is you would sketch a line, and then you would try to find 2 points that it kind of looks like it's going through, and then you would calculate the rise over the run. And in this case, it does look very close to a 45-degree angle. That's probably very close to a slope of 1. I'm doing perfectly. I'm hitting the corner of all the squares. So again, rough estimating slope, kind of working around the value of 1. If you just keep that simple in your mind, it's just everything seems to kind of come into place as it should when you're talking so in depth about this slope to the tangent, which are all these slopes of all these lines. Okay, so let's play around with another example. So that really should be a very brief and exact review, a little bit of slope here. So here's another good question. It says, find the function's graph at the given point. Find the equation of the tangent line. Here we go. Find the equation of the tangent line to the graph. I'm going to put to the curve. Sometimes they say graph and sometimes they say curve. You'll hear both of those words used quite frequently. At the point, let me find the point, 1, negative 1. Okay, so this is almost identical to the last question, maybe a little more detail. You know, the A, B, and C is kind of already integrated into the question. So the original function, the original curve is y equaling x minus 2x squared. So the original curve that's graphed out there somewhere is a parabola who is concave down, okay, because you have this x squared, this negative 2x squared in this equation, so you know it's some parabola out there concave down, and I'm looking for the slope of the tangent lines all over that curve. So to do that, I'm going to use the limit now. I'm not waving the magical wand anymore, but to do that, to find the slope of the tangent line anywhere along that parabola, it is the limit as h is approaching 0 of f of x plus h, this is called the difference quotient, minus f of x over h. So that curve is given to me as y equals. To kind of play around with this difference quotient, I'm going to put it in function notation. So this means that f of x is the x minus 2x squared, which is that parabola, the original curve. And my f of x plus h, which I have to put into that difference quotient, is going to be x plus h minus 2 times x plus h squared. And I usually do this off to the side before I plug it into the difference quotient because I think it makes it a little clearer, a little less messy, I hope. So this is x plus h minus 2 times, when you expand this binomial by using the FOIL method or I think some of y'all do the thing called the box method, something like that, then you're going to get x squared plus 2hx plus h squared. That means I just did x plus h times x plus h, which was the FOIL method to come up with that trinomial. One more step. This is x plus h, and I'm going to distribute the negative 2. This becomes a negative 2x squared minus a 4hx minus a 2h squared. A mess. A whole bunch of stuff sitting there. A bunch of x's and h's and 4's and 2's and whatever. And all of that's going to have to be plugged into this difference quotient. And I just hope I have given myself enough room to make it happen. So this difference quotient now equals the limit, as h is approaching 0, of f of x plus h, which is now what we just calculated. The f of x plus h is x plus h minus 2x squared minus 4hx minus 2h squared. That's the f of x plus h part, minus f of x. And f of x is x minus 2x squared. All of this over h. Just a lot of algebra. Trying to keep your x's and your h's clean enough that you know what you wrote. So this now equals the limit as h is approaching 0. Let's see here. This is going to be minus x plus, I guess I could write that down. This is x plus h minus 2x squared minus 4hx minus 2h squared minus x plus 2x squared all over h. And I will get to the point where I skip that step, do it more using mental math. Yep, we hope a lot of stuff's getting ready to go away. X is gone. It's going to zero out, right? And the 2x squared is going. And then if you look, pretty much everything left has the h in it, which is good because your goal is to get that h to factor and reduce. So this now becomes the limit as h is approaching 0 of h minus 4hx minus 2h squared, which I'm going to go ahead and factor it, which becomes h times 1 minus 4x minus 2h. Okay, of the 3 terms remaining, I pulled an h out, leaving behind a 1 minus 4x minus 2h. There you go. This is the goal. These guys need to go, or I cannot use direct substitution. The goal is for the h to factor so that it will reduce. Now when I evaluate the limit, I put the h value of 0 in and end up with 1 minus 4x. So when you evaluate the limit, when you find the slope of the tangent line, it is an expression. It's not a number yet. It's an expression which will tell me the slope anywhere on the curve. Anywhere on the curve. Every single tangent line to the curve, I can find the slope of it based on this expression. So there's the general expression that's going to give me that result. So then they're going to say, what is the slope of the tangent line? Now that you can do it anywhere on the curve, now I'm going to select the place where I want you to do it. I want you to find it at that point up here, 1, negative 1, where the x value is the positive 1. So find the slope of the tangent line where x is positive 1. That's the way we write it. The slope of the tangent line where x equals 1. So we go to our expression that we worked so diligently to come up with, which is 1 minus 4x. And I replace the x with the 1 and get 1 minus 4, which tells me the slope of the tangent line to that parabola, which was concave down, at the point 1, negative 1 is a negative 3. So you could almost say this is like answer part A and answer part B. These are the significant, most important results of our work. Then if they ask me the equation of the tangent line to the curve at that point, okay, at that point to the curve, the equation of the tangent line to the curve at the point 1, negative 1, I now know the slope at that point, the slope at x equaling 1 is negative 3, and my point is 1, negative 1. So using that point slope formula, y minus y1, which I didn't have room to write on the last example, but that's the formula that we all know that I'm using. So it will be y minus y1, which is y minus a negative 1, equaling a slope value of negative 3 times x minus x1, where x1 is 1. So when I clean this up, this becomes y plus 1 equaling a negative 3x plus 3. And when I subtract 1 off of each side, I get a negative 3x plus 2. That is the equation of the tangent line to the curve at the point negative 1, at the point 1, negative 1. Again, an entire page of algebra with 3 very important results that you need to understand what the results mean. Now, I should have done this before I came to class, and I didn't. But what I'd like to do is don't lose sight. This was the original curve. We have 2 equations on this piece of paper. The equation of the original curve, and now the equation of one of the many, many tangent lines to the curve. Okay, so you have 2 equations on this piece of paper. You need to be certain you know the difference in the 2 and what you're doing. So I'm going to pull the calculator up real quick and just see if this is going to work. I don't know if this is going to work or not, but it's worth the time to try it. If I go to my calculator, here it is, and someone's doing matrices on it recently. Let me clear it. Go away. It is so sluggish. Why is it not clearing? Quit. Thank you. Okay. Go to the, let's graph this thing. So our original curve was x minus 2x squared. And I don't know, I'll just do a zoom standard to make a relatively small window. See what the graph looks like. There's the graph. Yes, I was right. It was a parabola that was concave down. Now, there is a point on this curve, 1, negative 1, that has a tangent line. And we just determined that the equation of the tangent line to the curve at the point 1, negative 1 was a negative 3x plus 2. Oh, this is so sluggish. I have to be very patient with every click of the button. And I'm going to, I can't even see it. I was going to make this a dotted line. There it is. Okay, now graph it. And there it is. Okay, so here is our original curve. The dark one is the original curve. This is the tangent line. The dotted line is the tangent line to the curve, whose equation is negative 3x plus 2. And right here at this point, 1, negative 1, is where that tangent line is supposed to just barely be touching the parabola.
How did you get the tangent line to show up again?
Oh, how to make it like dotted or something?
Yeah.
Right here, you see when you get to the left of the Y, it has many options, and you just keep hitting enter until it gets to the version where it's dotted like that. Okay? So that actually graphed beautifully to try to get a vision of why you have 2 equations. You have your original curve and you have your tangent line. This tangent line will change all along the curve. We just found one of the many we could have come up with. That was kind of fun. That worked. Okay. Wrong screen. Here we are again. Lots of algebra. None of it is difficult. It does require some precision. You do need to be very careful when you're doing these. Okay, so let's do another example. Again, pushing hard that you're being careful to be accurate as you're evaluating these limits. Not that they're difficult, but oh, you get off just a little bit and then it's very frustrating. Okay, suppose we're doing the same thing. Find the equation of the tangent line. And to write an equation, you need a point in the slope. Okay, so there's our original curve, y equaling 1 over x minus 1. It's not a parabola. This is a rational function. It's going to have a vertical asymptote at x equaling 1. Okay, it's not a very pretty graph. It can be kind of confusing. That's your original curve. Find the equation of the tangent line to the curve. They haven't told me enough information. There's a whole bunch of tangent lines to this curve, infinitely many of them, right, at every point on the curve. So what additional information must they give me? Some point. Okay? So here we go. So suppose they do it at x equaling 3. Now you've given me enough information to actually answer your question. They need to tell me at least this much. Okay, so to find the equation of the tangent line, again, you must have two things. You must have the slope, which is that limit we're going to do, and then you must have a point. And the point is the point where x is 3. What's the rest of the point? What's the y value of this point? 1/2, because when you put the 3 in, you get 1 over 3 minus 1, which is 1/2. Okay, so there's your point. You're going to find the slope by doing the limit. Your point, you had to kind of finish it out, but now you go through all the page of algebra with the limit to find the slope. So this slope is determined by finding that limit. Okay, that's the goal. That's kind of giving you a mental version of what you're getting ready to do. So here we go. I'm going to have to find the limit. To get the slope, I'm going to have to find the limit as h is approaching 0 of what they call the difference quotient. And everything's kind of in function notation. So I'm going to rewrite this. Instead of y equals, I'm going to write it as f of x equals 1 over x minus 1. So I can use direct substitution to the difference quotient, and it all kind of flows more smoothly for me. And then the f of x plus h is going to be 1 over x plus h minus 1. So you can see already this is not going to be pretty. This is going to be a very ugly complex fraction. Not that it's difficult, it's just going to be very complex. So here we go. When I substitute this into this limit becomes the limit as h is approaching 0 of f of x plus h, which we just wrote as 1 over x plus h minus 1, minus f of x, which is 1 over x minus 1, all divided by h. So you can see, oh, this is not fun. Okay. So going back to that whole process of I've got to put those two, the numerator of this complex fraction, I've got to add those two suckers together. You're going to have a common denominator. That denominator is going to be ugly. Okay, the new denominator is actually x minus 1 times x plus h minus 1, a bunch of stuff. So this is now the limit as h is approaching 0. The new denominator in the top of the complex fraction is going to be x plus h minus 1 times x minus 1. On both of these, x plus h minus 1 times x minus 1. Big, ugly stuff here. And this is all over h. Okay, so the first fraction's denominator changed by adding the binomial x minus 1 to it. So this one I'm going to multiply times x minus 1 over x minus 1, making this numerator a 1 times x minus 1. The second fraction I actually had to multiply times x plus h minus 1 over x plus h minus 1, which makes this new numerator x plus h minus 1. Not difficult, just be careful. Lots of little things going on, lots of little details. So what do we have? This is the limit as h is approaching 0 of x plus h minus 1 times x minus 1. And this will be x minus 1 minus x minus h plus 1. When you distribute the subtraction, this is going to become minus x minus h plus 1. All of this is still over h. And we're doing all this because we're looking for that expression which represents the slope of the tangent line anywhere along this curve. Keep in mind what's going on. So now this is the limit as h is approaching 0 of all of this stuff up here, still over x plus h minus 1 times x minus 1. Okay, so we have this x and this x kind of zeroing out. We have this negative 1 plus 1 being 0, so all we have left is a negative h, right? That makes us happy. It's supposed to make you happy. Now with this complex fraction, I'm going to multiply the bottom. This is like the major division bar, the big one. So I'm going to multiply the bottom and the top times 1 over h. So then these h's go, the denominator becomes 1. So this is the denominator of the complex fraction becomes 1. So this becomes a negative 1 over x plus h minus 1 times x minus 1 all over 1. Big change in those two steps. Finally, we have a situation where h is not dominating the denominator, making it such that I cannot use direct substitution. At this point, I can finally put the h value of 0 in to this limit, and no longer as a limit, I'm going to actually evaluate it as negative 1 over x plus 0 minus 1, which makes an x minus 1 times x minus 1, or negative 1 over x minus 1 squared. That is an expression which is going to tell me the slope of the tangent line anywhere on the curve. So remember, doing the limits giving you the slope of the tangent line. Keep that all straight in your mind. So you might even write this, the slope of the tangent. Don't lose sight of what you have after all this work. Okay, lots of algebra. None of it, again, is difficult. Just you have to be careful. Okay, so we can kind of call this the result of all of our initial work. If you want to call it A, but that's the punchline of that work so far. So now, they want me to know the slope of the tangent line at that point where x equals 3. So I have the expression. This is going to be negative 1 over 3 minus 1 squared, which is a negative 1 over 2 squared, which is a negative 1 over 4. And then if they want the equation of the tangent line, to the curve at x equaling positive 3, I have now the point, which is 3 1/2, the point on the curve itself, and the point which is actually on my tangent line also, because it's where they meet. And I have a slope of the tangent line, this tangent line, at x equaling 3 equaling a negative 1/4. Then I go in here and I use y minus y1 equaling m times x minus x1. So this becomes y minus 1/2 equaling a negative 1/4 times x minus 3. And I'm going to have to almost wave a little bit of a magical wand here myself and do a lot of mental math as I'm at the bottom of this page. So this becomes y equaling a negative 1/4 x plus 3/4, plus a half, which is 3/4 plus 2/4, which, am I right in saying 7/4? Am I doing that right? Be 3/4 plus 2/4, 5/4. Okay. There it is. That one might not be so pretty on the calculator because the original curve has a vertical asymptote. But keep the vision in your mind of what you are accomplishing. You're accomplishing a lot of important stuff. Okay. And it's fun. It just takes a lot of work on your page. It seems to be a little bit time-consuming. Okay. This is another common question that you need to be very comfortable with. And you seem to be comprehending well kind of what we're doing. You're not just going through the motions. You seem to be grasping the concept, which is good. And here's another question now. It says, at what points along the curve, and remember when they say curve, this means some original function that's been graphed, okay? At what points along the curve are their horizontal tangent lines. And here's the curve. X squared plus 4x minus 1. So there's your curve, and the question is, where are you going to get a horizontal tangent line to that curve? Okay, so your first thought is, I wonder what this is. Oh, this is a parabola, right? Is it concave up or concave down? It's concave up because that coefficient of x squared is positive. If I really wanted to graph it by hand, I could find the vertex, that negative b over 2a thing, right? Or you could complete the square and get this thing in the x plus h squared minus k thing. Remember all that? Way back there, okay? It's been somewhere in my head, but I know it's back there. So we can kind of get a vision of this, and in fact, I kind of sketched it before coming to class, and it looks something like this. Okay, it looks, I don't know, something like that. Now, where in the world on this curve would I have a horizontal tangent line? At the vertex, right? So if you're kind of visualizing your tangent lines, okay, and I didn't graph this very well because I'm not really showing symmetry. Okay, but there's a tangent line, and here, let me see, there would be another tangent line right here, approximately like this. Okay, and then there would be another one here. But there's only one place where it's going to be truly horizontal, and that's going to be right here at the vertex. Okay, that's the one. That's the one where the slope is 0. That's that horizontal line. So there is one point along this curve, it's going to be at the vertex, that you're going to have a horizontal tangent line. So now it wants me to figure out that point. So how do I figure out the point? Well, what you want to do is, if you know that the slope of the tangent line is found by doing this lovely limit process as h is approaching 0, you know what? I think I'm getting ready to run out of ink. Like, how many times have I done that without losing my pen? Okay. We know that's what the slope of the that's how we find the slope of the tangent line. And we want that slope now to equal 0. Wherever that thing equals 0, that's going to tell me the point on the line where I have a horizontal tangent line. So that's what I'm doing. So I need to do the limit. Remember, this is going to come out to be an expression with the x variable in it. So when I set that expression equal to 0 and I solve it, it's going to come up with an x value. And that x value is going to be the x value right here at the vertex of the parabola. Okay, projections, thinking through what you're going to be doing. Okay, so again, here we go. So if we rename this f of x, this is f of x now equaling x squared. Oh, this is going to be big. This is going to be pretty, yes. Okay. This is going to be joyous, right? Okay, so f of x plus h is going to be x plus h squared plus 4 times x plus h minus 1. We can do this. It's just going to be time consuming. So when I expand this binomial using FOIL or the box method, wherever you're familiar with, it's going to be x squared plus 2hx plus h squared. I'm going to change pens. This is wanting to kind of give on me. That's not going to work. Y'all might not see it, but it's not being smooth. And then distribute the 4. You're going to get a 4x and a 4h minus 1. And none of those are like terms. None of it. What a mess. Okay, so this is, it's not hard, but it's, oh my. Oh boy, are we having fun yet? Okay, so I'm going to need a lot of space. So over here, the slope of the tangent line is the limit as h is approaching 0 of f of x plus h, which is all of this stuff. X squared plus 2hx plus h squared plus 4x plus 4h minus 1, that's f of x plus h, minus f of x, which is x squared plus 4x minus 1 all over h. Boss, some stuff better zero out. Okay, so now the slope of the tangent line, which is the limit as h is approaching 0 of this mess, okay, is going to be, when I do, is going to, I better do it, x squared plus 2hx plus h squared plus 4x plus 4h minus 1 minus x squared minus 4x plus 1. We better get 2 or 3 things at least going away here, right? X squared's gone, the 4x is gone, and the 1 is gone, and all that's left are terms that have h in them. Okay. There you go. All that's left are terms that have h in them, which is what you're kind of expecting to happen. So this becomes the limit as h is approaching 0 of 2hx plus h squared plus 4h all over h, which is going to factor for me beautifully, as h is approaching 0, of h times 2x plus h plus 4. And now we have succeeded at finding a way of reducing this thing so h is no longer in the denominator, so that now I can use direct substitution and put an h value of 0 in, which gives me the result of 2x plus 4. So that is the expression which will tell me the slope of the tangent line anywhere along the original curve, which we kind of really rough sketched up there as a parabola whose concave up. So the question was, at what points along the curve is there a horizontal tangent line? Well, we want to know the x value of the point. Well, if it's a horizontal tangent line, then the slope of the tangent line, this 2x plus 4, would have to equal 0. The slope of the tangent line would have to equal 0 if it's a horizontal tangent line. Okay? The slope of the tangent line would equal 0 if it's horizontal, which would mean that 2x plus 4 would have to equal 0. So therefore x would have to be what? I know, I thought that thing, the half came into my mind very quickly. So that's the answer to the question. But did it work? Well, the way to find out if it works or not is to graph that original parabola and see if we're on track. Let me see. Let's go back to that. At what points? I guess I have to get the y too. Okay, so here we go. Go down. Clear all this mess off. I'm going to get rid of that. Okay, so what did we have? X squared. Squared. Plus 4x minus 1. Okay, I'm going to graph it, and I think I'm still under the zoom standard window, which is fine because, well, it's not fine. Okay, the vertex is way down here, right? So I need to drop the window a little bit. Okay, so I'm going to do, what, a y min of, instead of negative 4, maybe it should be a negative 10. I was on a zoom standard. What was wrong with it? I know, I wonder why it changed. Okay, so right there, right, should be an x value of 2. So let's see. So what did I say? X value was negative 2 second. Calc. Put a value in of negative 2 and see if it lands at the vertex. Yep. So we're good. That's for your horizontal tangent. What would be the name of the horizontal tangent line? Okay. We'll play with this. Y equaling negative 5, and we will animate it. There it goes. Yeah, I think it's because of this program up here. It's like every time I try to hit the key, I have to be so patient because it takes it forever to go in. But there's your and the only horizontal tangent line there's going to be to the curve is going to be at that vertex. Isn't that cool? So that gives you kind of a visual that, yep, we're on track, we did it. And also, we just figured out what the y value was. It was -5. Aren't we so smart? Break our arm patting ourselves on the back, right? Okay, I'm going to pause the recording and let y'all run take a break real quick. Okay, so let's take a look at another example. This one algebraically is going to have some radicals in it. So that's really the only difference. Kind of the same thing, but we're going to play around with the radical to make certain you are good with this algebraically. So again, find the equation of the tangent line.
So the tangent line, that's the derivative?
The derivative is the slope of the tangent line. Okay? So find the equation of the tangent line having, yes, I sure can maximize this screen. Remember, that limit's giving you the slope. Find the equation of the tangent line having a slope of 1/4 to the curve y equaling the square root of x. Okay, so in this case, they're not telling me to find the slope of the tangent line and then the equation. They're saying you figure out where that tangent line is such that it will have the slope of 1/4, and then you give me its equation. So in other words, we're kind of having to find the point on the curve who has a tangent line whose slope is 1/4 to kind of go through this process. So now, and we have a radical, which is really why I pulled this example and have chosen to go ahead and do this, even though we've worked so hard so far in this concept. So let's play around with the radical. So what we're going to do is we're going to go ahead and evaluate the limit, which is the slope of the tangent line. And once we've come up with that expression, we're going to set it, after we do all this algebra, we're going to set it equal to that 1/4. And when we set it equal to the 1/4, remember it's going to be some expression with x. And when it equals 1/4, we'll solve it and come up with the x value, which is the point on the curve where the slope of the tangent line is 1/4. So that's kind of what we're playing with. So let's go ahead and put this in function notation to kind of keep it with this difference quotient. So f of x is the square root of x, and then f of x plus h is going to be the square root of x plus h. So this is going to kind of be a new approach on the algebra when we plug it into this difference quotient. Okay, so let's see what this is going to look like. So we're going to have the limit as h is approaching 0 of f of x plus h, which is the square root of x plus h, minus f of x, which is the square root of x, all over h. So we cannot evaluate this limit because we have the issue where we cannot put the 0 into it using direct substitution because it causes the denominator to be 0. So what is the algebraic method with all these radicals? What did we do? Multiply it times conjugate. There's the word. The conjugate of that binomial, which is, it was a minus sign, now it's a plus. Okay, so this becomes the limit as h is approaching 0. When I do the FOIL method or the box method, whatever you're doing with two binomials, the numerator is going to become x plus h. The o and the I are going to zero out in the FOIL method, and the square root of x times the square root of x is just x. And go ahead and leave the denominator alone with all the lovely radicals. Don't try to multiply this out, just leave it alone. Yes?
For the function of x plus h, why does the h fall under the square root? Isn't the h independent of...
No, it's not. It stays underneath there because you're replacing all of x with x plus h. Okay, so it stays under that radical. All right, so this becomes the limit as h is approaching 0. The x's are going to go, which is nice, leaving this as an h over h. So that we can, this is not bad at all. Those h's are going to cancel, and we're going to be able to evaluate this really pretty quickly. So again, as we want, we get rid of that h in the denominator so that now we can use direct substitution. When you put an h value of 0 in, this is 1 over the square root of x plus the square root of x, which is 1 over 2 square root of x. So that will tell me the slope of the tangent line anywhere along the curve, the original curve being y equaling the square root of x. This looks more complex than the original curve, but who cares? It just happened to work that way. So we now know that the slope of the tangent line to this curve, anywhere along this curve, is represented by this expression. Now the question given was a little bit of a twist on what we have been doing. It says find the equation of the tangent line having a slope of 1/4. So they're forcing the value of the slope upon me, meaning that this slope has to equal 1/4 by the given information in the question. Okay, this is the first time they've done this to us. So we set it equal to 1/4. Well, what's going to happen now is we're going to solve this and come up with an x value, and that x value is the point on this curve where the slope of the tangent line is 1/4. So now we have this. Anybody know what to do with this equation? Cross multiply. So when you cross multiply, just like a proportion, a ratio equaling a ratio kind of setup, you're going to get 2 square root of x equaling 4. You divide both sides by 2, and the square root of x will equal 2. Then you pretty much square both sides, and x will equal 2 squared, which is 4. Okay, and this is the x value at the point on the curve y equaling the square root of x, where the tangent line has a slope equal to 1/4. That's what we just accomplished. That is the x value of the point on the curve where the slope of the tangent line is 1/4. So the point itself is 4, and then y equaling the square root of 4, or you could say 4f of 4, going back to the original curve, which is 4 square root of 4, which is the point 4, 2. So trying to get an image of this in your mind, a visual perspective, y equaling the square root of x, the original curve looks something like that. Okay, that is f of x, or y equaling the square root of x. The original curve. The point 4, 2, wherever it is, I don't know, maybe it's right there. Okay, at the point 4, 2 is where the slope of the tangent line to the curve is going to equal 1/4. That's kind of the visual now. So the question still is, find the equation of the tangent line. Find the equation. Well, this was always like part C of everything we've done. The equation of the tangent line means it requires us to have the point and the slope. Well, we have the slope was 1/4. That was actually given to us. And now we have the point, which is 4, 2. So then we go to the y minus y1 equaling m times x minus x1. This now becomes y minus y1 of 2 equaling a slope of 1/4 times x minus 4. Y equaling 1/4 x minus 1 plus 2, which is a plus 1. There is the equation of the tangent line to the curve who has a slope of 1/4. Okay, so just a little bit of a change in the way the question was asked, making certain that you're very comfortable with knowing the procedure, knowing kind of how you should approach it and what your results should be and why it should come out like that. Right. Now, the other things they run into in this section, I didn't realize just how long this section was going to be, but another important part of this section which you're going to see quite a bit in calculus in your future also, is what we refer to as rate of change. Okay, the rate of change. And rate of change is equivalent, that's an F. Rate of change is really equivalent to slope, which now in calculus is going to evolve into the slope of your tangent line at a point. Okay, this is where this is all going to evolve. You're looking for the rate of change, which is going to be equal to slope, which is going to go into the slope of your tangent line at a particular point on the curve, which then becomes written as instantaneous, what a word, rate of change. Because instead of rate of change being the slope of a secant line, we are landing it using the limit as being at only a 1 point on the curve, because we're looking at it as the h value becomes 0, or as the distance between two secant points becomes nothing. So there's no distance in between them. So this goes back, I can show you again back in the book if you would like to see this. I guess I've never really have shown this to you, but they're really pushing. I'll just show you real quick to verify what I've already shown you. They're pushing this first derivative symbol now, equaling your limit, the derivative of the function, which now is going to become known as the difference quotient with an increment or a difference of h. Okay, and then going into the rate of change. Okay. Okay, here's kind of where they talk about it up here too. It says if we interpret the difference quotient, and we're talking about the difference quotient, difference meaning subtraction, quotient meaning a fraction, all of this here is your difference quotient. Okay, this fraction is now what they're calling your difference quotient. And it says if we interpret, right here, the difference quotient is the average rate of change, the derivative gives us the function's instantaneous rate of change with respect to x at a point. And what this is going to turn into now is kind of working with velocity. Okay, velocity is also rate of change, which is also slope at a point on a curve. So this is going to again evolve now into what we call velocity. So we're going to see a little bit of word problem now, and I'll write it down so that you don't have to have the book, but I'm pulling this really straight from the book. And here's what the question looks like, and here's my reference. This is actually number 27 on page 104 in the book. So if you go into my math lab to take a look at this, the question says, an object is dropped. An object is dropped from the top of a 100-meter tower. A 100-meter tower. Its height, its height above the ground, the height of the object as it's falling, the height of the object above the ground as it's falling, after t seconds is determined by the following function, which is 100 minus 4.9 t squared. So we can find the height of the function by using that expression 1 minus 4.9 t squared, where t is the number of seconds it's falling. So now the question, and if you want to, you can put height equals ht equals, so that kind of has a little better understanding. So then the question finally is, how fast is it falling? Okay, how fast is it falling 2 seconds after it is dropped? 2 seconds after it is dropped. 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 2 all this has a little more personal understanding to me because I actually went skydiving last December, November, something. It was fun. I was falling, they said, at 120 miles per hour. Is that what they said? I think that's what they said. It was not scary at all. It really was not. It's not like a roller coaster because you fall at a steady rate. So once you get to that rate, it's just very loud as the wind goes across your ears. The fun part is when they pull the chute and then you get to kind of play, you know. So I didn't do it by myself. I could probably have done that, but it was fun. Okay, so when they ask how fast, that is velocity. And velocity is going to be kind of like slope. So really, we have height of this object from the ground as it's falling equaling 100 minus 4.9t squared. To find velocity, you're going to take the first derivative of the height, which is going to give you rate of change, which is going to tell you how fast it's falling. So we're going to use this. If you want to, we can change this to y equaling if you want it to make it look kind of more familiar with just the variables and so forth that we've been using so far. You can do this. And so we're going to end up finding the velocity is going to equal the limit as h is approaching 0 of f of x plus h minus f of x all over h. Okay, and when you plug all this in, and I have done all this, and it's not difficult, it just takes a lot of work. When you do this with this function, it's going to equal, after a page of algebra, a negative 9.8x, and you're just going to have to believe me because we're running out of time. This lecture is getting very long. So when you actually evaluate that limit using this function, this is what you're going to get, which we're going to equate to the velocity of the object as it's falling. So remember, this is the slope of the tangent line, which is the velocity of the object as it's falling. Now, when we put an x value in, that's how many seconds this object has been falling. So how fast is it after 1 second? How fast is it falling after 2 seconds? How fast is it falling after 3 seconds is what this is going to tell me. So the question is asking how fast is it falling, or what is the velocity? Okay, which is the velocity after 2 seconds. The velocity after 2 seconds. So you just plug a 2 into this negative 9.8, and when you do, you're going to get a negative 19 meters per second is how fast it's falling. Now, really, speed is supposed to be a positive value. Dropping is going to be negative and going up would be positive. Really, the direction is what determines being negative or positive. So really, when you're talking about speed, you really want the absolute value of that number. So we really go ahead and write 19 meters per second. Okay. So I did a lot of, right here, of algebra that we just kind of missed. But we've done a lot of algebra already in this class showing you how to evaluate that difference quotient in order to be able to come up with that result. Okay. All right, and I think that you'll be comfortable with most of those questions from this point forward. So I'm going to actually let this be the end of this section. Nice long section, algebraic, not difficult.